Welcome back. Let's continue our discussion of functions. Looking at graphs, here are two more graphs, and we're going to determine do we have a function or a relation, why, and then determine the domain and the range for each. Let's take number 3. We've got this nice little curvy graph here. Is it a function or a relation? In the last video, we used the vertical line test, so let's try that again. For the vertical line test, we just draw vertical lines anywhere on the graph, and the vertical line must intersect the graph no more than one time. If a vertical line intersects the graph no more than once, then we have a function. So each vertical line here only intersects the graph one time, so we have a function. Even though it's not explicit in this particular graph and in number 4, these graphs go on forever in the directions that they're headed when they leave the graph. So we can't graph them because they keep going on forever and ever. Why is it a function? Every input has exactly one output. Every vertical line intersects the graph at most once. Either of those reasons is perfectly acceptable. And now we can talk about the domain and the range. Let's start with the domain. In the last video, we talked about smashing the function onto the different axes. The x for the domain and the y for the range. So we can play the same game here, working on it visually, and we're going to do a straight vertical smashing. So there's no spreading like there is when we squish Play-Doh and it goes from a small cylinder to a much larger cylinder. We're playing a mind game here and imagining this, but we're just going to smash it onto the x-axis and then determine what part of the x-axis gets covered by that graph. So let's try it. We're going to push the graph onto the x-axis, and these arrows at the end, arrows come up or down onto that x-axis. They're pretty much showing that the coverage of the x-axis is complete. It goes on forever and ever. So looking at this, if we had our number line for x and we tried to color it in based on what we had, we would color the entire x-axis graph, or the entire x-axis number line. When we color the entire number line gets covered. X can be any number. We could say x is a real number. Another fancy symbol we can use, x is an element of the real number set. Mathematics is a language of symbols, and mathematicians have symbols for practically everything. And the real number set is definitely one of those that has its own symbol. It looks like an R with an extra bar on the left. It's just our symbol for the real numbers. So for an inequality, we don't really have one. We sort of do, I guess. We could say that x is less than infinity and greater than negative infinity. X is less than infinity and greater than negative infinity. So that could be our inequality. That infinity symbol is that sideways 8, meaning infinity. Interval notation. Again, we're covering the whole number line, so we're going from negative infinity to positive infinity. Can we ever reach the end of these number lines? No. So we cannot ever contain infinity. We can never reach it, so we can't contain it. So we're going to use parentheses in this case to indicate that there's not really an end point. We can't go on forever. Well, we can't ever reach the end, so there can't be a hard stop at the end. Infinities will always be accompanied with parentheses. Now let's look at the range. We'll take the graph and we'll trash compactor smash the graph onto the y-axis this time. And when we smash it onto the y, just like before, these endpoints also get moved. And notice the entire y-axis gets covered. And since the entire y-axis gets covered, We have the same situation with our range. This time, though, we're going to use the letter y instead of x, y representing our range. And so then we also have the exact same interval as our domain. Our domain is all real numbers, and our range is all real numbers. Now let's shift to problem number 4. Here we have a different type of graph. First question, do we have a function or a relation? We can start drawing vertical lines, and notice how many times the vertical line intersects the graph. So the first one, none, none. Oh, this one's got 2, and then a lot of the other ones intersect the graph twice. And we discovered before that's not so good. This is a relation. Domain and range. I'll let you consider the squishing or the smashing onto the axes. See if you can come up with the same domain and the range that I will. Domain is -1 to infinity, and the range is -infinity to +infinity. Again, see if you can make sense of the domain and the range for number 4 and how it matches up with the graph. Moving on to problems 5 and 6, I'm going to let you work on 5 on your own. See if you can come up with the domain and the range for 5 and determine if it's a function or a relation. 6 is a little different, and to trace the graph so you can see why, this graph has a break in the middle. And we'll talk a little later about what causes that break when we talk about our families of functions. There is a reason and a purpose behind it. But this will also create a different situation with our domain. So first question, is it a function? Do the vertical lines hit the graph in exactly one place? And we do have to be careful with this one, mostly because our lines that we draw have thickness, but real lines in mathematics should not have any thickness to them. They only have length. Thinking about this that way, even though it may look like, especially close to the y-axis here, that those vertical lines might hit more than one point, they actually don't. They only hit the graph in one point. This is a function. We still have that vertical line reasoning, or every input has exactly one output. Our domain, again, we're going to take that graph and smash it onto the x-axis. Notice that these places up top, this almost looks like a chimney in a way. It keeps going on forever, but it never crosses the y-axis. They just follow it and get closer and closer and closer to the y-axis without ever reaching it. If we're talking about the y-axis, what does x equal on that y-axis? X equals 0. So we have every value of x represented except for 0. Our domain is all x values except for 0. We can write that interval. I'm going to need a little more space. This is a bigger interval. We'll have -infinity. We go up until we hit 0, but we don't ever reach 0. We're going to pick 0 back up. We're going to go hop over the y-axis, hop over x equals 0, and go back to infinity. So we have a number line for x that basically looks like this. We're coloring everything on the axis except for 0. A big whole open circle on 0. In order to indicate that these two interval components are together, we use this symbol called a union. It looks just like a capital U, and that's our interval for the domain. Range is a little bit simpler in the sense that we have our y-axis, here's our x-axis, and when we compress the graph onto the y, everything gets colored except for y equals 0. But we don't go below into the negative values. Just like these pieces around the y-axis follow the y-axis and never cross it, these pieces near the x-axis follow the x-axis and never cross it. So for our range, y is strictly greater than 0. And when we can create an interval That's 0 to infinity. We never go less than 0. Moving to symbols, we can define a relationship between these variables x and y. We've been using them for the graph. Let's go ahead and use them for our symbols. To find out if an equation defines y as a function of x, so remember y is the output and x is the input. So we want to be able to put in a number for x and get out a number for y. In the first example, you see y minus x squared equals 2. We have an equation with x and y in it. To determine if it is a function, we solve for y, so we add x squared to both sides, and we get y equals x squared plus 2. Because we have one y value for every value of x, we can pick a value of x, plug it in, and it determines a y value. One y value. We have a situation that y is a function of x. Looking at example 2, if we try to solve for y in terms of x, we subtract x squared from both sides, and then we take the square root to get rid of this y squared part. We end up with this equation, y equals plus or minus square root 4 minus x squared. We will be working with these square roots a little bit later on in the chapter on radicals. So if that's not familiar to you right now, it will be. The thing to notice here, though, is if I plug in a value for x, let's say something like 0, let's go simple, y equals plus or minus square root 4 minus 0 squared. We can simplify it out. Plus or minus 4 minus 0 is 4. Square root of 4 is 2. But because of that plus or minus in the front, we have 0 going to both 2 and negative 2. We do not have a function. One input is going to 2 outputs. Taking a look at some function notation. A function is a rule assigning exactly one value in the range to one value in the domain. If we have a function rule, then we can use what's called function notation. All this is replacing the y variable with a new symbol read f of x. This is not multiplication. This is not f times x. This is a name of a function, f of x. We could change the letter f to be something completely different. You'll see g, h, p. We could use any name we wanted to. In using this notation, we're able to see the value of the input and what the output is that's corresponding to it. So we'll see a little bit later what that means. Down here at the bottom, here's an example. We have the equation 2 minus 3x equals f of x. So f of x is defined to be 2 minus 3x. 2 minus 3x is the rule for the function. And f of x is the name of the function or the output or the y value.